Hello. Today we will be looking at the concepts for Chapter 10, and those will be over rotational kinematics and energy. The big ideas here are that these rotational quantities we're going to talk about have a correlation to the linear quantities. So each rotational quantity actually corresponds to a linear quantity. So a lot of this is going to look familiar. We'll just be using different variables. Second is that rolling motion is actually a combination of linear and rotational motions. And third, a rotating object will have kinetic energy just like any object that is in linear motion. We see rotational energy all around us, from the wheels on our car to celestial bodies. Objects everywhere are experiencing rotational motion. So, to actually describe this, we need to define position, velocity, and acceleration for these rotating objects as opposed to objects that are moving in a straight line. So, we're going to start with angular position. And in linear motion, we would use a coordinate system to define a 0 point where x equals 0 or y equals 0. In rotational motion, however, we're going to use the angular position to do this. And that position is represented by the variable theta. And theta is going to be the place where we define it to be 0. So that our reference line is the point where it equals 0. So for example, here, we'll say this point is 0. And once this wheel has made a full turn and comes back, it would be, it'd be 360 degrees, though we won't be using degrees very often in this unit. We'll be using radians. When we see that theta is greater than 0, please note that we'll be moving counterclockwise from our reference line. But when we see theta less than 0, we're moving clockwise from our reference line. And I just mentioned this on the previous slide, but one complete revolution in circular motion is 360 degrees, though I think you are all aware of that. This, and I can write this down for you. I think that'll be very helpful, actually. This actually equals 2 pi radians, in case you have forgotten that. I mentioned already that angular position is measured in radians. Well, a radian is the angle for which the arc length on a circle of radius r is equal to the radius of the circle. Okay, let me say that again. It is a point where the arc length, so this point here, is equal to the radius r of our corresponding circle. And this allows us to relate radian measurements to a corresponding arc length. So for a single radian, for 1 radian, so I'll write that here. 1 radian, we're going to see that S is equal to R. So the arc length will be exactly equal to the radius. For 2 radians, it would be S is equal to 2R. For 3 radians, it would actually be S equals 3R, and so forth. So hopefully you're seeing the connection there. So for any random angle, we're going to use this. We're just going to say that S is equal to R times theta. That's a simple relationship, but it's not true when we relate it to degrees or revolutions. So this is only for radians. Again, 1 revolution is 360 degrees, which equals 2 pi radian. So I'm going to write that down again. 1 revolution equals 360 degrees, and that is equal to 2 pi radian. Nope, that's 2 pi radian. And if we did this math, we would find that 1 radian is approximately 57 degrees. But all of these units are dimensionless that we are talking about, so you'll just be writing, 1 or 2 pi, pi over 2, something along those lines. Or if we're talking about revolutions, you would just tell me how many. Now that we've seen and defined angular position, let's go ahead and define angular velocity. During any rotational motion, we will see a change in the displacement. So we're going to see a change in that angular displacement, which would just be theta final minus theta initial. We can take that change and divide it by the time that has passed in order to find our average angular velocity. And the units for this are going to be in radians per second. But when we write that, we don't actually write the word radian. We just write seconds to the -1 or inverse seconds. Oh, and the symbol here for average angular velocity is omega. And then we'll put AV after it because we're also going to look at an instantaneous velocity. Yeah, we're going to do that right now. We can find the instantaneous angular velocity by looking at smaller and smaller changes in the time until, as time approaches 0, we'll be able to get a better idea of what our instantaneous angular velocity is. We're going to use the same formula, and their units are the same as well. The only difference here is that, again, we're using a smaller period of time, and we've taken away the AV that was after omega here. So it's just omega. And a quick thing to note is that anytime we refer to just angular velocity, we are talking about the instantaneous velocity, not the average. Okay, and finally, we can find the angular acceleration. So to find this, we might need to know how long it takes for an object to complete an entire revolution. And the time to complete one revolution is called the period, and it's represented by the letter T, a capital T, not a lowercase t, that's for time. Angular acceleration is just how quickly our angular velocity changes with time, and that's going to be measured in radians per second squared instead of meters per second squared like we would see in linear motion. And this is represented by alpha. And notice again that we put AV after it to indicate that it is an average. Just like we did for angular velocity, we can find the instantaneous angular acceleration by taking a time that is close to 0. So same formula, same units. So same formula, same units. Here again, we see that we've just written alpha instead of alpha with an AV as a subscript. And over here, I wanted y'all to make note of something. So anytime we see that angular velocity and the angular acceleration moving in the same direction, whether they're both positive or both negative, we are going to see an increase in the speed. However, when they are in opposite directions, when the velocity is moving clockwise and the acceleration is moving counterclockwise, or vice versa, we will see our speed decreasing. We can actually take our average angular acceleration equation and rearrange it to find that omega is equal to omega naught, so that initial omega, plus alpha times t. This should look very familiar to you. It should look a lot like one of the equations of motion, specifically this one. So you see we're going to have a lot of relationships here, and hopefully this unit will make a little more sense because you've already seen a lot of this stuff before. We've just switched out a few of the terms and variables. Each of these rotational variables relates back to its linear motion counterpart. We have x and theta, so in linear notation we would be using x, and for angular it would be theta. The velocity for linear is just v, but in angular velocity it is omega. And then we also see acceleration, which is a in linear motion, and it is alpha in angular motion. And here I've just switched out the variables in my equations of motion to match what it should be in linear motion. So this would be good information for you to have written down. Anytime something is moving in a circular motion, at any instant of time, that object is moving in a direction that is tangential to the circular path. And to find the tangential speed of any rotating object, we can take the radius and just multiply it by the angular speed of the object, like so. This is always going to be measured in meters per second. So again, a unit you are very familiar with. So for speed, even when we're talking about rotation, we're still going to use meters per second. So it's our radius multiplied by omega, which is the velocity, the angular velocity. We need to make a slight adjustment in order to find the centripetal acceleration. And remember, this is just the acceleration that is in the direction of the axis of rotation, or the center of the circle in layman's terms. So it's the force this way. The centripetal acceleration is like this. And the only change we've made from here to here is that we are going to be squaring the omega term. So centripetal acceleration is the radius times omega squared, and that is measured in meters per second squared. And the tangential acceleration, which is the acceleration caused by a change in speed, can be found by multiplying the radius by the angular acceleration. So r times alpha. The difference between tangential and centripetal acceleration is actually quite simple. A changing angular speed is going to cause our tangential acceleration, but it is a changing direction of motion which will cause centripetal acceleration. Here we have a child on a merry-go-round. If the angular speed is increasing, that child is going to experience both a tangential and a centripetal acceleration. If that's the case, then our total acceleration is going to just be the sum of the individual accelerations. So it would be our acceleration tangential plus our acceleration centripetal, and that would equal the total acceleration here. Motion caused by rolling is slightly different than the circular motion we've talked about so far. Why? That's because our axis of rotation will also be moving. So not only is this wheel going to be turning, but since it's moving forward, we're going to see this axis of rotation, the center of the circle, moving forward or potentially backwards, depending on what is happening. Either way, it is moving. Since we see both linear and rotational motion here, so linear motion for this part and rotational motion for the actual wheel, we call that rolling motion translational motion. Translational motion. But no worries, we can relate that translational movement to the rotational movement. The time required to complete a single revolution, t, so our period, is related to how quickly the axis is moving, the translational speed of that axis. In order to find that speed, we say v equals 2 pi r over t, but we can simplify that even further because we know that omega is just equal to 2 pi over t. So when we replace 2 pi over t with omega, we just find this, that our velocity will equal our radius times omega. Rolling motion can also be considered to be two pure forms of energy. Two pure forms of motion. That's pure rotational motion and pure translational motion. So what does that mean? In pure rotational motion, we see the velocities at the top, so here and here. The top and the bottom of the wheel are moving in opposite directions. One is moving forward and one is moving in the opposite direction. That could be vice versa as well. In pure translational motion, each point is going to move with the same speed in the same direction, as we see here in this image. Rolling motion is just, well, it can be considered as a combination of these two types of motion. For any mass that's rotating in a circular motion, we can find the kinetic energy that is associated with it. So we're going to swap out our linear velocity term with the angular velocity term, because normally we would have kinetic energy equals 1/2 mv squared, but we are talking about angular motion. And over here, we see v equals rw, not w, r omega. So we're going to replace v, so we know v equals radius times omega. Let's use that here. And then we're just going to rearrange it a little bit to find 1/2 mr squared multiplied by omega squared. And in this case, now this mr squared term is taking the place of our mass, and that's going to be important to remember. Since the mr squared term plays the part of mass in our previous equation, okay, so we saw that this is the equivalent of this, and omega squared is the equivalent of our velocity squared. We actually call any mass that is rotating, or we say that any mass that is rotating has a moment of inertia. And that moment of inertia is represented with the letter I, or the variable I. So if we just replace that piece of information, go back again, where is it? Right here. We're going to replace mr squared with I. And when we do that, we now get that kinetic energy is equal to 1/2 times I, our moment of inertia, times omega squared. The larger our moment of inertia is, the lower the speed will be. And the smaller that moment of inertia is, the higher our speed will be. And this has units. Moment of inertia has units of kilograms times meter squared. So here are the units for I. The shape of any rotating object is going to affect its moment of inertia. And here I've included a few shapes that might rotate and the formulas you would use to find the moment of inertia. So here we see a hoop, and it's I equals mr squared. Whereas if we have a solid, it's a solid hoop, I mean, it's a disc, we're going to add this 1/2 term. And you're not going to be able to see that later, so I should probably erase it. Okay. And I've included a few more, some spheres, hollow and solid. I've changed the axis of rotation, etc. As always, energy must be conserved, even during rotational motion. And the total kinetic energy for this motion is going to be the linear and the rotational energies added together. So the linear term plus the rotational term added together. And we can see that here with this formula. Since linear and angular speeds are related, we can simplify this expression. Well, I don't know if you'll call this simplified, but we can combine this expression together just a little bit more. Recall that velocity is equal to r times omega. We can rearrange that to say omega equals v over r and put that into our original equation here. When we do that, we can start rearranging, and it's very obvious here because we just added it in, but we can rearrange to find this equation here. And feel free to do that yourself, and if you're struggling to rearrange that, I would be happy to explain that as well. And finally, I'm going to say this again, and I'll write it down this time. The faster an object is traveling, the smaller its moment of inertia will be. So small I equals larger velocity, and a large I, or moment of inertia, equals a smaller velocity. So if we have these two objects, we have the hoop and we have a disc. We want to know which would actually make it to the bottom of this ramp first. So take a moment and think about that and hit play when you're ready. Well, these objects have equal mass and equal radius, so we know that will not play a factor. That means the one that has the smaller moment of inertia is going to make it to the bottom first because it will have a higher velocity. Well, let's go back and look at our equations. So we have this, we have a hoop, and we have a disc. Which would have a smaller moment of inertia? Well, for the hoop, we see it's mr squared, but for the disc, we have 1/2 mr squared. So we're going to have the mr squared term, but we're dividing it by 2. So the moment of inertia of the disc is going to be smaller than that for the hoop, meaning this disc is going to make it to the bottom first. So the disc would be our winner here because it has a smaller moment of inertia. You can also think about this in terms of potential and kinetic energies. The two objects have the same energy to begin with, but after that motion begins, the object with the larger momentum is going to have less energy left to give to translational motion and will therefore move at a slower speed. So again, in this case, no matter which way you look at it, the disc is going to beat the hoop to the bottom of this ramp. And these last 4 slides are just a summary of everything that we've talked about, so you can review this as you need to. And again, these are great things to have written down on your formula sheet when you take your test. I will be back in the next video with the concepts. So thank you for watching.